This is lecture 23 on urban transportation planning. The discussion on trip distribution analysis will be continued in this lecture. Before we proceed further, let us briefly recollect what we did in the previous lecture. You may recall we tried to understand the application of the gravity model with a numerical example in the previous class. On completion of the problem, we discussed about the calibration of gravity model, and as you may recall, calibration of gravity model means determining the parameter value related to Fij, the friction factor. And when we discussed about the different forms in which Fij can be expressed, we found that Fij can be expressed as a function of travel time, because normally trip distribution is done using segmented data based on mode used for travel as well as based on trip purpose. So, once you use segmented data based on mode, the travel time is going to remain a constant, travel cost is going to be a constant because it is mode specific, right, and other related factors like comfort, convenience, level of safety, all these factors will remain unchanged. So, that is how we felt it is appropriate to express Fij as a function of Tij, travel time. We also discussed about travel distance as a substitute for travel time and understood that it is not appropriate under urban condition to substitute travel distance for travel time because of variations in the characteristics of the road, network and related factors. Okay. And finally, we discussed about the calibration procedure recommended by BPR, Bureau of Public Roads, USA. As per BPR method, we assume different functional forms for Fij based on the distance of travel. We segment the travel data based on distance as travel involving travel time of or travel distance of certain segment. If you segment the data based on travel time, you can say all trips involving travel time between 0 and 5 minutes, then all trips involving travel time between 5 and 10 minutes and so on, right. And then we develop trip length frequency distribution curve both for model calibrated value as well as field observed value, and then compare both the trip length frequency distribution curves for matching. If the curves are not matching, we just modify the value of Fij using an appropriate modification procedure and continue the process until there is a reasonable match between the two trip length distribution curves, right. So, that is how we do the calibration as per BPR method, right. And if you look at the basic structure of the gravity model itself, you may recall this was the basic structure we initially adopted. Tij to be equal to k times Pi Aj whole divided by Wij raised to power c. This is simply the replication of the equation related to Newton's law of gravitation. We have replaced m1 and m2 by Pi and Aj, right. R squared in the denominator is replaced with Wij raised to power c. K is proportionality constant as we had in the earlier equation also, and we modified this equation by introducing a constraint related to trip reduction. Since we know Pi is equal to sigma j is equal to 1 to n Tij, we introduce this constraint into this basic equation and finally obtained this formulation of gravity model. Tij is Pi Aj Fij divided by sigma j is equal to 1 to n Aj Fij. This is a very simple formulation of gravity model without consideration to the zone to zone adjustment factor, which is Kij. And we need to understand that we have introduced one constraint here, namely Pi to be equal to sigma j is equal to 1 to n Tij to get the final equation for the gravity model. So, rightly we can call this gravity model as singly constrained gravity model. What did we do with the other constraint related to trip attraction Aj? We satisfied that constraint by iterative process when we distributed the trips. You may recall we did several iterations to adjust the cell values along each column to be exactly equal to the attraction values, right. Finally, we need to satisfy both the constraints related to Pi and Aj, right. But here the model formulation itself has inbuilt constraint, which is only one constraint. That is why it is called a singly constrained gravity model. The other constraint is taken care of while we actually distribute the trips, and it is possible to incorporate both the constraints at the initial stage itself and straight away do the distribution process without any iterative procedure involved in getting the trip distribution values. And such a model is named as doubly constrained gravity model, because both the constraints are put into the model formulation at the beginning itself. And this is the general formulation of the model, and the explanation for the notations used or given here. Tij as usual is the number of trips produced in zone I and attracted to zone J, and Pi total trip production at zone I, Aj total trip attraction at zone J, Xi is trip production balancing factor. We need to balance the trip production such a way that there is no distortion in the trip production values of each of the zones after distribution. So, that is taken care of initially, and Yj is trip attraction balancing factor to take care of the constraint that trip attraction of each of the zones is not changed after we distribute the trips, okay. And Dij is a distance or travel time between zones I and j, mostly travel time as we have discussed, and alpha the parameter to be estimated, right. This is a very general formulation of doubly constrained gravity model and Xi and Yj can be written as follows. Xi is written as 1 by sigma j equal to 1 to n Yj Aj Dij raised to power alpha, okay. And Yj is written as 1 by sigma I is equal to 1 to n Xi Pi Dij raised to power alpha. So, we have the formulations for Xi and Yj, and we have the general formulation of the gravity model involving Xi and Yj. Now, how to go about substituting the known values and getting the value of Tij, trip distribution between zones I and j, is the question. Please note that equation 2 involves Yj, and equation 3 involves Xi, right. We are trying to express Xi in terms of Yj and then Yj using Xi, right. Once you change the value of Yj, Xi will get altered. Once you change Xi, it will have an effect on Yj, right. And the procedure followed in the analysis is as follows. While we just calibrate the doubly constrained gravity model, the parameters are found by iterating independently for convergence. First we take the equations for Xi and Yj, right, iteratively see that there is no change when you repeatedly calculate the values of Xi and Yj, so that there is a stabilization. That means the two constraints are taken care of initially and then substitute back the values of Xi and Yj in the parent equation. This is what we do. Initially, after assuming a trial value for alpha, alpha is the parameter to be estimated, Dij raised to power alpha. For example, Yj can be taken as 1. You assume some trial value for alpha, that is one step. Then assume initially for convenience Yj to be just unity, some value you can take, and the value of Xi is determined using the earlier equation or using equation 2. Then the value of Xi can be substituted, right, to get the value of Yj using equation 3. Clear? And this process is repeated until the values stabilize without much of change. When you repeatedly substitute for Xi and Yj, you will find that at some point of time there is no change at all, it is stabilizing. Then those values of Xi and Yj are fit for substitution in the parent equation to get the value of Tij. Then the values of Tij are calculated using the doubly constrained gravity model given as equation 1. The results are then given in the form of a matrix as we normally do to facilitate comparison with the observed trip distribution, which is also normally given in the form of a matrix. So we are going to have two matrices, one based on the gravity model, the other one based on the field observed data, right. Have two matrices and we have to compare two matrices for matching. Clear? So that is the calibration process. Then the value of alpha is varied. See, this process is based on one initial value of alpha that we assume, right, and we are not sure whether that alpha is perfect or representative of the field condition. So it is better to have a set of values of alpha, and then for each case you just compare your model, simulated and field observed matrices, and then choose the one or choose the value of alpha which gives the least error in matching of the two matrices. That is why we need to have more values of alpha and do the same iterative process with each value of alpha range to produce a series of gravity models, right. For each value of alpha, the difference between the observed and calculated values in each of the cells of the trip distribution matrix is determined, and the degree of closeness of the observed and calculated values are expressed using suitable statistics. Please note, calculated values as well as observed values in each of the cells of the trip distribution matrix is compared and the variation is determined. okay. Cell 1 1 in gravity model matrix and corresponding cell in field observed matrix, compare both the numbers, find the difference. So, like that you compare cell by cell of the two matrices and then get some indication of the match level of match of the two matrices. And there are statistical procedures available to get the degree or level of match of two given sets of data. Obviously, the value of alpha pertaining to the minimum error condition is taken as the optimal value, right. And these are the statistical measures used for comparison of the two matrices. I am not going to give the basic theoretical background or the proof of this formulae. I will be just giving you the result. It is up to you to refer a suitable book and try to understand the theoretical background as well as the related proof. Okay. There is one statistic named normalized phi statistic, and this is the formula to calculate the value of phi, where Tij, as you know, is equal to observed trip interchanges between zones I and j, observed values as you observe in the field. T star Ij, model simulated trip interchanges between zones I and j, right. So, Tij values you pick from the matrix that you develop based on observed data, and T star Ij values you pick from the matrix that you develop based on your gravity model result, right. And T is a mean observed trip interchanges between zones I and j, mean of all the observed values, that you can easily calculate, and that is what is given here as T. Then there is another statistic used for the same purpose, comparison of two sets of data, which is named as normalized mean absolute error. A normalized MAPSER, that is how it is abbreviated, is equal to n square into sigma over I sigma over j of absolute value of Tij minus T star Ij whole divided by T. Of course, notation explanations are same as we have seen earlier, there is no difference at all. And coefficient of determination, nothing but r squared, about which you are familiar, but the formula used is slightly different, but gives you the same result. R squared is given as 1 minus sigma over I sum over j of Tij minus T star Ij whole squared divided by sigma again over I, then sigma over j Tij minus T whole square. T is the mean value, mean observed value. Okay. We have three statistical measures available for comparison. We can use any one of them or use all the three and then take an overview of the comparison and choose the alpha value which gives you the least error. Is that clear? So, with this basis, let us take a small numerical example and try to understand the procedure of calibration of doubly constrained gravity model. Calibration of doubly constrained gravity model. I am going to give the example in the form of a figure, so that straight away we understand the given situation clearly. You can see totally there are 5 traffic zones shown here in the picture, zones 1, 2, 3, 4 and 5. Zones 3 and 5 shown in red color are residential zones. implying that there will be only trip productions from these two zones. Zones 1, 2 and 4, which are shown in green color, are employment zones. There is going to be only trip attractions related to zones 1, 2 and 4. The numbers shown in parentheses between the zones are the actual travel time in minutes for movement from one zone to other. Also, please note that zone 3, for the purpose of trip connectivity, are connected directly with zone 2, zone 1 and zone 4, right. There is no connection of 3 with the other zone, namely 5. Okay. Similarly, zone 5 is connected to 1, 2 and 4, right. This is how the zones are connected, and the trip production and attraction values are as shown here. P3 is 300 trips, P5 700 trips, A1 450 trips, A2 250 trips and A4 300 trips. You can assume in this case also that these trips are specific to a particular mode. With that understanding only we are proceeding further and for a particular purpose, right. Now, let us consider a doubly constrained gravity model with function of travel resistance as dij raised to power alpha. This is our consideration. We can consider different functional forms. In this case, we just assume the frictional resistance to be following a simple polynomial form, right, dij raised to power alpha. Then we can write the doubly constrained gravity model as Tij to be equal to xi pi yj aj dij raised to power alpha, and we know xi is given as we have seen earlier to be equal to 1 by sigma j is equal to 1 to n yj aj dij raised to power alpha, and yj is nothing but 1 by sigma over I xi pi dij raised to power alpha, right. As we discussed earlier, we are going to work with equations 2 and 3 first with an assumed value of alpha and some assumption for yj, and try to balance equations 2 and 3 and then substitute the values of xi and yj in equation 1 with one assumed value of alpha. That will be one trial. Then we will change the value of alpha and go through the same process and then get back to the original equation and get another set of model simulated values, right. For the given example, this is how we can write the xi equation or equation pertaining to xi. X3 can be written as 1 by a1 y1 d31, isn't it. Dij is 31 here raised to power alpha plus a2 y2 d32 raised to power alpha and a4 y4 d34 raised to power alpha. 3, as I said earlier, is connected to what are the other zones connected to 3? 1, 2 and 4. That is how we are dealing with d31, d32 and d34. Clear? And x5 can be written as 1 by a1 y1 d51 raised to power alpha plus a2 y2 d52 raised to power alpha plus a4 y4 d54 raised to power alpha, because zone 5, which is a production zone, is connected to zones 1, 2 and 4, is not it. Y1 can be written as 1 by x3 p3 d 31 raised to power alpha plus x5 p5 d 51 raised to power alpha, and y2 on the same lines you can write as x3 p3 d 32 raised to power alpha plus x5 p5 d phi 2 raised to power alpha, and y4 is 1 by x3 p3 d 34 raised to power alpha plus x5 p5 d phi 4 raised to power alpha, and of course the values of d 31, 32, 34, phi 1, phi 2, phi 4 are given. Just it was given in the figure, again I am repeating the same numbers 3, 2, 5, 3, 5 and 4, right. So, we are going to assume some value for alpha as well as yj and work with equations 2 and 3. And to make the understanding easier, I am giving this information. If the values of yj and alpha are taken as unity, then we can write equation A as given by equation B. You may wonder as to how to choose the value of alpha to be unity suddenly, why not some other value? Are we sure that assumption of unity value for alpha will give us a rational result? Based on practical experience, planners have fixed some range for the value of alpha. When you express friction factor as a polynomial function of travel time or travel distance, the alpha value normally falls within a range. Okay. That range will be normally known to the planners. Okay. That is how we take some trial value of alpha initially, maybe lower bound or upper bound, clear. So, that is how you need to accept or understand the fact that we are taking the value of alpha to be just 1, and value of yj being taken as unity is just for convenience, we are taking it, and then during iterative process automatically it will get changed. Okay. We can write equation A as given by equation B. Equation A is nothing but the same equation that we have seen earlier pertaining to x3, it is nothing different, simply 1 by a1 y1 d31 raised to power alpha plus a2 y2 d32 raised to power alpha plus a4 y4 d34 raised to power alpha. Now, simply substitute the values of alpha and y as unity, you get this equation. You can write x3 to be like this, very simple equation. That is what we are going to do. We are going to substitute the corresponding, these values are known to us now, is not it. We can find out x3 because we know the value of a1 as well as d31, right. a2 d32 is known, a4 d34 is known to us. So, we can substitute the values and get a trial value for xi, then this value will go into the equation for yj, then we will come back to the equation for xi and repeatedly do the exercise until there is not much of change in the result. First iteration, taking alpha and yj raised to 0 within parenthesis, just to indicate that it is the first attempt, 0 has got no other meaning, right, to be equal to 1. We have taken both alpha and yj to be 1 and start with the first iteration. As I indicated to you, x3 is simply 1 by the corresponding attraction value and distance plus corresponding attraction value plus into distance plus the attraction value and the corresponding distance. Are you able to appreciate this particular equation for x3, right? And similarly x5, substitute the corresponding values and get the result. please note that we have gone up to 8 decimal places. That is a level of accuracy expected, otherwise we will not be able to get consistent values for yj and xi. Okay. If possible, we can even go up to 10 decimal places or 12 decimal places if you want to be more accurate. Okay. I have stopped with only 8 decimal places here, right. y1 0, on the same lines we substitute the known values and we get a value of 1.21759924, again holding the same number of decimal places. y2 0.90896109, y4 substituting the corresponding values we are getting 0.8441646, right. With this we are completing one iteration and we have to move on to second iteration, and we are not going to change the value of alpha at this stage, it is going to remain same until we get a consistent value for all the x and y's, xi's and yj's, right. You can see the difference here. What I do here is x3 I calculate as 1 by the corresponding attraction value, the next number is nothing but the corresponding travel time for that link, and then I put the y1 value which we have got in the previous iteration. Earlier this was not appearing in the first iteration because we have taken that as 1 unity, right. Now we have got some value for y1, right. That is how I have written that. I have not really substituted the value, it is understood. Once you substitute that value you are getting this result. Okay. For want of space I have not substituted the actual calculated value in the previous iteration, right. So we just substitute the actual value of y10 here, plus 250 into 2 y20 plus 300 into 5 y40. If you do so, you are getting a value of x3 to be 0.00029722, that is the value of x3. On the same lines proceed with the other calculations. x5, again substituting y10, y20 and y40, you get x5 value to be 0.00026365. Then y11 will be 1 by x31. Please note it is not x30, x31 because we have just got x31 value. So you can use that immediately, right. x31 can come into this calculation because we already have the value calculated using y10, y20 and so on. So we can use that current value here, x31, then the corresponding production and then the distance, plus x51 into 700 into 3, and you get a value of y1 to be 1.21779299, and y21 on the same lines we get the value to be 0.908185898, and then y41 0.8445637. Clear? Now third iteration, repeat the same. We have now the value of y1 available to us to calculate x3. So latest value of y we are putting in the subsequent calculations, and x5 we calculate as shown here, and y1, please note we are using x32 because just we completed the calculation of xi. So, put that value and get the value of y1 and y2 and then y4, clear. And fourth iteration, you may wonder why we are going on doing iteratively. This implies that there is no consistent value of xi's and yj's obtained so far. Maybe little later I will show you the comparison, right. x5 we calculate as given here, and then we calculate the value of y13, y23, y43, and go ahead with fifth and sixth iterative steps also. On completion of fifth iteration and sixth iteration, you may get a set of values for the xi's and yj's. I will just show you the result of fifth and sixth iterations. This is the value of x3, okay, 4 you are getting on completion of fifth iteration, right, and x5 value is this, y1 this much, y2 and y4. Then let us do the sixth iteration also and get the corresponding values. Now we are getting x3 5 value to be this much. Now look at the two numbers that we have obtained through iteration 5 and 6. What is the variation? Still they are not the same. There is variation in the 8th decimal place. Okay. It is up to us to say yes or no. Okay. I think all of you are inclined to say almost yes. Okay. Let us see the result of other calculations. x5 4, there is a perfect match, no variation at all up to 8th decimal place. y1, there is variation in the last decimal place, right. y2, there is variation in the last decimal place, and y4 there is a perfect match. Okay. Shall we say that we have converged on the correct value of xi and yj? As I said, the right way is proceed further and see whether the convergence is still possible or we are tending towards divergence. Normally in practice, when there is a match up to 6th decimal place, in practice the planners accept the consistency of xi and yj and substitute the values of these factors in the parent doubly constrained gravity model. Okay. So, we will say that this consistency is acceptable and we can use these values in the gravity model. It can be seen that the values of xi and yj have stabilized without much of change, that is important. Okay. Using these values of xi and yj in the equation for Tij, we get trip interchanges as follows. Now only we go back to equation 1 for Tij, substitute the values of xi and yj because we have the values here, right, and then we have assumed alpha value to be unity, that remains, okay, and substitute those values and get the result of Tij, okay, T 31, 32, 34 whatever exchanges are there we can get, and I am giving you directly the calculation details as well as the result. So, T31 is going to be x3 p3 a1 y1 d31 and the values are known. So, what we do is I am just giving you the result only, not the details of calculation. Only thing is to emphasize the point that we cannot have fractions in the final result. I have rounded off the value to the nearest whole number. We are getting 146.57129540 and so on, and we just round it off to 147. T32, in fact it is T star 32 because it is model simulated value to differentiate between Tij and T star ij, and we get 40.48 and we just simply round it off to 40, right. You may ask me why not 41, okay. You must take an overview, look at the other numbers and check whether our rounding up procedure in this case is right or wrong, okay. T star 34, 112.9457 can be obviously rounded off to 113. T star 51, 303.4287 rounded off to simply 303. T star 52, 209.51 rounded off to 210. T star 54, 187.05 rounded off to 187, right. Now, you must also see that these numbers are not violating the total of the values initially given to us, okay, total production and total of attraction. Keeping that in mind, you must be careful in rounding off exercise. That is why particularly, even though you can round off 0.48 to be 0.5 and then round it off to 41, I am just leaving it as 40 mainly to take care of the constraints related to Pi and Aj, okay. So, this is the resultant matrix. Please note that these numbers were given to us, right. P3 was 300, P5 was 700, A1 was given to us as 450, A2 250 and A4 was given to us as 300. Had I changed this 40 to 41, we will have problem here, right. So, that is how I said when dealing with large number of cells you should be careful in rounding off and see that we are not violating the constraints related to Pi and Aj. Still in most cases you will be able to logically round off the fractions to nearest whole number, clear. So, this is how we get the theoretical matrix, and this has to be compared with the actual matrix, and then based on the statistics we need to check whether the assumed value of alpha is right or not. So, this is one exercise as I said. Similarly, we need to assume different values of alpha, maybe 1.5 for second trial, 2 for third trial, 2.2 whatever for fourth trial and so on, and then choose the alpha value which gives the least error, okay. To understand this process, let us take a case study, so that we have a feel of applying this model for a real life situation. And case study pertains to the city which is already known to you, so that you are more comfortable and understand the situation in the field. And the study city considered is Tiruchirappalli city in Tamil Nadu state, India. Okay. Some basic information about the city. As I mentioned to you earlier, there was only one mode of public transport, which is bus, and private transport modes available were car, motorized two-wheeler, bicycle and foot, right. Foot of course is truly a private transport mode, is not it. And intermediate public transport, IPT, or taxi, auto rickshaw and cycle rickshaw. Trip purposes, as we have seen earlier, work, education and others. We have classified the trips into only 3 categories because the percentage of trips made for other purposes was how much? Anybody who can recollect the number? Hmm? 6%. It was only 6%. 49 for work, 45 for education and just 6% for all other purposes, okay, as far as this particular city is concerned. Okay. And total number of zones, traffic zones in the study area were 85 traffic zones. You may recall that I mentioned to you that the population of city at that time was around 1 million. It was not exactly city, the population of the study area, which includes the surrounding panchayats, town panchayats, etc., where from there is a regular commuting by people into the city center. It was just 1 million, and number of traffic zones is just 85. If you look at this number in comparison with the division of urban area into traffic zones for study internationally, this is a very small number. Ideally, the number of traffic zones should have been a minimum 200 traffic zones, that is it in an international standard. Okay. And why then only 85 traffic zones for this case? What might have been the constraint, or what is the problem with less number of zones? What is the real technical problem when you divide the area into a smaller number of traffic zones? It is very simple. Please remember, we consider zone centroids as the points of origins and destinations of trips. If you have a large area for zones, you will have only one point as the exact point of trip origin and trip destination, is not it? But in practice, it may not be exactly matching with the reality, right. You may combine Velachery, IIT campus, Adyar area and Saidapet all together and fix one point maybe near Anna University as the point of trip origin and destination, which is unrealistic, is not it? The land use also may not be that homogeneous, clear. So, that is how larger zones will produce unrealistic results. So, you should have zones of compact and homogeneous land use of manageable size, okay, normally around 1 to 1.5 kilometer radius, the general zone size, except in cases where you have a vast area of just barren land in the fringe areas of your study earmarked for your study in case of some cities. Otherwise, zone size should be as small as possible, so that you get accurate results replicative of the real travel pattern, clear. So, please understand 85 is not internationally accepted number, but still we have done it because of the constraints related to cost. when you divide the area into more number of traffic zones, you are going to collect more segregated data, employing more people, spending more money, spending more time, right. That is the reason why the number of traffic zones have been reduced to only 85, but still we can appreciate this effort, because at that point of time this kind of comprehensive transport system study was done only for few cities in our country. Even today I would say that systematic comprehensive transport planning study has been done only for few cities in our country, the mega cities and few other cities like Hyderabad, Bangalore and so on. Other cities are just managing without proper database for transport system analysis and planning. Clear? In that background, if you look at this effort, it is really good. Tiruchirappalli is a very small city compared to the other urban areas. So, that way there is really a good sincere effort, and it was divided into 85 traffic zones, and there were 49 traffic zones in the urban area, and rest of the zones were in the area surrounding the municipal boundary. Clear? So, with this basic information about the study area, we will stop for today, and to check what we have done in this class, you may recall we have just very briefly discussed about the difference between singly constrained and doubly constrained gravity model. The constraints are mainly related to trip reduction and trip attraction. In the case of singly constrained gravity model, which we have used earlier, the constraint related to trip reduction was put into the model before the model was applied for distributing trips, right. Whereas in the doubly constrained gravity model, we put both the constraint at the initial stage itself and then finally use the gravity model for distribution of trips, so that in one go you get the distribution result in the form of a matrix. Okay. And checking for the correctness of the trip distribution is based on comparison of your model simulated and field observed trip distribution matrices. Clear? With this we will close for today, and we will continue our discussion in the next class.